carbon dioxide. Let me write it. Write with me. Carboxylic acids lose carbon dioxide to form hydrocarbons when their sodium salts are heated with soda lime. That means NaOH, sodium hydroxide, and calcium oxide, CaO, in the ratio of 3:1. Now let me complete this within bracket. In the ratio of 3:1. So when NaOH and CaO combine in the ratio 3:1, the combination or mixture of this sodium hydroxide and calcium oxide is called soda lime. So basically what happens after adding this, and then there will be elimination of CO2 to form hydrocarbons, and this reaction is known as decarboxylation. This reaction is known as decarboxylation. Is that clear?
Yes, sir.
So please do write it. Let me know when you are finished with this. Then I'm going to explain the reaction.
Yes, sir, done.
Very good. So you know what is carboxylic acid salt, right?
Yes, sir.
Okay. So this is your carboxylic acid, and if you want to write the formula of carboxylic acid salt, so just remove hydrogen and add metal like NaK, sodium, potassium, magnesium like this, and this is your carboxylic acid salt, and you are going to pass it or react it with soda lime, that means NaOH and CaO, and after reacting this with this, you are going to do hydrolysis. Then you know what will form. This Na2 will combine itself to form Na2CO3, and this R will be directly converted into alkane. Just take an example. If you have CH3C-ONA and you are going to react this with soda lime and hydrolysis, this CH3 will combine with H, and the rest of the product will be converted into sodium carbonate. So as we just started, please do write it, and if you don't understand it, please do let me know. After this chapter, I want to start that coordination compound. Do let me know when you are done with this. Are you done with this?
Yes, sir.
Pause.
Yes, sir.
Very good. Now see, the next is basically we need to study the chemical reaction of carboxylic acid. And this is your substitution reaction in the hydrocarbon part. In the hydrocarbon part of carboxylic acid. So in this, we have the first, that is halogenation, and this reaction is very important and it is also called name reaction. And the name of the reaction is Hall-Volhard-Jelinski reaction. So I'm going to write a point about this. Please do write with me. So in this reaction, basically carboxylic acids having an alpha hydrogen, that we have already discussed what is alpha hydrogen in aldol. Alpha hydrogen are halogenated. One alpha hydrogen will be halogenated. That means there will be replacement of hydrogen with chlorine or X halogen at the alpha position. At the alpha position. At the alpha position. On treatment with chlorine. On treatment with chlorine or bromine. Chlorine or bromine in the presence of a small amount of red phosphorus to give alpha halocarboxylate acids. And this reaction is known as Hall-Volhard Jelinski reaction.
सर वो स्मॉल अमाउंट के बाद क्या है?
A small amount of red P for phosphorus.
Okay.
So are you going to give today's mock test?
Sir, maybe because I think I will go.
Maybe you think? Will you give today's mock test? Oh, Nafisa,
Yes, sir.
are you done with this?
Yes. Yes, sir.
Was
Yes, sir.
so see the reaction is very easy. In carboxylic acid, let's say this is your carboxylic acid, CH2, C double O H, and you are going to react this with halogen X2 in the presence of red phosphorus. Red phosphorus. And in the second step, you are going to do the hydrolysis. So see what you need to do. Just see, this is your functional group. This is your functional group, and this is your alpha carbon. So it has two hydrogen. That means two alpha hydrogen is there. So what you need to do, just replace one of the hydrogen. So it becomes one hydrogen. Replace one of the hydrogen with this X, and here what you will get halocarboxylic acid. X is basically equals to chlorine and bromine. It is only for chlorine and bromine. And its name will be alpha halocarboxylic acid. Alpha halo. Alpha halo.
Sir, after removing hydrogen, what to do?
After removing hydrogen, if you are removing something, you need to add. So this is your what alpha substitution reaction. So one of the X will go and replace hydrogen. Let me know when you're done with this.
Yes, we do.
So I'm going to give you a question on this. CH3 is CH2 C double OH, and you are going to do this in the first place, in the first step and second step.
Sir, it will be CH3, CH, and then down is X,
X.
and
Let's say
then
it is Cl2 in the presence of red phosphorus in this.
Cl2.
So can you
Cl.
name it? Can you name it? Can you write the IUPAC of this?
Yes, sir.
Please do.
Sir, it will be 2-chloropropanoic acid.
Very good. 1, 2, 3. So it will be 2-chloropropanoic acid. Boaz got it?
Yes, sir.
Please do let me know when to change this slide if you are done with this.
Yes, done.
Are you done with this, Nafisa?
Yes, sir.
The last reaction of this chapter is basically the ring substitution. Ring substitution. It's very easy. The ring substitution. So if you are going to react this, as you can see, this is your COOH carboxylic acid, and if you are going to react this with concentrated H2SO4, HNO3 first, and then we can write either of them plus concentrated H2SO4. Then there will be generation of, then there will be production of an electrophile NO2 plus that will directly attack on meta position, not ortho and para, because an ortho and para is already having electron deficiency. That's why it will directly jump on the meta position. And in the same way, we can go for, you can see this is your COOH. And if you are going to react this with Br2 in the presence of Fe, Br3, there will be generation of electrophile. And due to presence of this COOH, which is electron ring deactivating group, so there will be deficiency of electron or ortho and para. So this will also attack on meta position. Its name is M-bromo. Its name is M-bromo benzoic acid, and its name is M-nitro benzoic acid. So here our chapters completed. Now I'm going to give 3 questions only, not for test. Just solve it right now and let me know. It is based upon a strong acid, a strong base, and then we are going to start chapter from second book, in the first book, which is coordination compound. So we are having only 2 chapters left. Today is 23rd. This chapter will be completed soon. Coordination compound. Then we will go with surface chemistry, which is a theoretical chapter. So I'll also provide some notes in PDF form, and then we will go with amines. And then all the best.
Done, sir.
Done, everyone. Lafisa.
Yes, sir. Done.
Very good. Please do write the question first. Which acid of each pair from here would you expect to be a strong? Would you expect to be strong? CH3CO CH. Wait a minute. CH3CO CH2F. The second one is CH3F CO2H CH. Wait a minute, this is 2 CH2 CH2 ClF CO2. The third one is CH2F CH2 CH2 CO2H. Or we can write CH3 CHF CH2 COOH. And in the fourth one, you need to go through this. This is your benzene in which CF3 is there and C double OH is there. C double OH CH. You need to compare it, please do.
Sir, the first one is the second option.
Very good.
Second one is F, the one that has F. Sir, the third one is the second option.
Very good.
The first option is the fourth one.
The fourth one, first or second?
First option.
Very good. See, for us, acidic character, acidity is directly proportional to minus, the one with high value of electronegativity, the one with highest electronegativity, and also proportional to minus. So see, there is no electronegative element, but here fluorine is the most electronegative element, so its acidic character is more. There is chlorine, there is fluorine. So fluorine is more negative than fluorine. So that's why it is. Now, fluorine is far away from here and fluorine is near from here. That's why this. Now again, fluorine is here and there is no fluorine here. Hydrogen is there. That's why this. Is that clear?
Yes, sir.
Yes, yes.
Wait. Both of you done with this? Pause.
Yes, sir.
Very good. No. You can see the chapter is completed. Now I'm going to share the new history for the next chapter that we are going to do is coordination chemistry. Wait a minute. Coordination compound. Can you see a new stream?
Yes, sir.
Wait a minute. Let's start with this coordination compound. So first of all, what is this coordination compound? Before that, I would like to introduce I would like to write the definition. Basically, when two or more stable salt combine to form a new compound which have same chemical properties in solid state as well as in solvent, that compound is known as coordination compound. That compound is known as coordination compound. So basically, I'm going to write the definition. Please do write with me. Compounds formed due to combination of two or more stable salts, two or more stable salts, which retain their property, which retain their identity or property in solid as well as dissolved state are called coordination compound, are called coordination compound. I'll give you example. First write it, then you will get it. Basically, whenever two or more salts combine, a compound is formed that is known as addition compound. That is known as addition compound, and these addition compounds are of two types. These addition compounds are of two types. The first one is double salt. The first one is double salt, and another one is coordination or complex compound. The another one is known as coordination or complex compound. Complex compound. So it's very easy basically. What I want to say is that whenever two or more stable salt combine, they form a compound that is called addition compound, and this addition compound are of two types: double salt and coordination compound or complex compound. So what is double salt and coordination compound? The salt or the addition compound which do not retain their identity in dissolved state or in solution, that is called double salt, and the one or the addition compound which retain their identity even in dissolved state or solution, that is called coordination. Is that clear?
Yes, sir.
Write it and
Yes, sir, done.
Fawaz, are you done with this?
Yes, sir.
Very good. Now I'm going to differentiate between these two, which is very easy. So basically, I'm going to write those which lose their identity. In solids. Like if I'm going to take an example of double salt, as you can see, let's take an example of more salt, that is NH4 whole twice, Fe, SO4 whole twice, dot 6H2. So if you are going to dissolve this in water, it will lose its identity and all these compounds will be converted into ions. Na2NH4 positive plus Fe plus 2 plus SO4, 2SO4 minus 2 plus 6H2. So if dissolved, it dissociated, that's why it loses its identity. But when we talk about this coordination compound, so basically those compounds which do not lose their identity in solution, their identity in solution, that is called coordination compound. As for example, if I'm going to take an example of a coordination compound that will come like this, that is like this K4FeCN whole 6. And if you are going to do hydrolyze or put this in solution, then it will be converted into 4K plus. But the square bracket, the groups that present in a square bracket will not be dissociated in this way. So if all the elements that is not dissociated, or you can see the square bracket is as it is, so that's why it doesn't lose its identity. Is that clear?
Yes, sir.
Please do that. Done, everyone? Nafisa?
Yes, sir.
Now we are going to talk about some basic terms. Before that, I will explain the terms, some basic terms, right? Some basic terms. So if you are going to talk about some basic terms, I'll show you what we are going to talk about. This is square bracket. Generally, these are denoted within a square bracket. If you have anything before a square bracket and after a square bracket, these are basically known as counter ion. These are basically known as counter ion, and they used to stabilize, or basically they used to neutralize the compound. Basically, if you have got positive charge on the square bracket, then this counter ions neutralizes that. Always remember, if it comes before the bracket, that is basically positive counter ion. That is basically positive counter ion. So if on a square bracket there is negative charge, this positive counter ions we can put here to neutralize it, and this is your negative counter ion. Wait a minute. So this is your negative counter ion. Or just let me know when you are able to see this screen. Fawaz and Nafisa.
Yes, sir, we can see it.
So basically, this is your negative counter ion. And when positive charge come on the square bracket, then this negative counter ion comes and neutralizes. As you can see on this, in this complex compound, there is negative charge. That's why this positive counter ion comes and neutralizes the compound. Are you getting my point? Nafisa and Fawaz.
Yes, sir.
Very good. Now see, it's very easy. And this, the number of positive or negative ion depend on the charge. If you have plus charge, 4 plus charge, then 4 4 negative charge, so plus 4 positive will come. Now see, after this bracket, you will get central metal atom. You will get central metal atom or ion. We call it central metal atom or ion. Is that clear? Please do speak up, Nafisa and Fawaz. Fawaz.
Yes, sir.
And after this, whatever is present is called ligand. Ligand is basically also known as here base. It acts as base and Lewis base, basically Lewis base. And this central metal atom is treated as acid, or you can call Lewis acid. Why it is so? Because here it accepts electrons. It accepts electrons, and here it donates electron. And according to Lewis acid and base, the one which donates electrons are Lewis base, and the one which accept electrons are Lewis acid. Is that clear? Is that clear?
Yes, sir.
And together this central metal atom and ligand are known as coordination entity. Coordination entity. Together they are known as coordination entity. So I'm going to again repeat it. The one which is before bracket or after bracket are counter ion. Before bracket, positive counter ion. After bracket, negative counter ion. Just before, just after this bracket is central metal atom, and after central atom, whatever is present, it can be 1, 2, 3, 4. That depends. That all are ligands. All are ligands. Ligands are Lewis base, and central metal atom are Lewis acid. And these ligands and central metal atom together are known as coordination entity. Please do write it and let me know when you are done with this.
Yes, sir, done.
Very good. What about you, Fawaz? Oh, wait a minute. I just want you to write this. I already have written the definition. It will save some of our time. That's why I'm doing this. Wait a minute, please. Some basic concept. So can you see the screen? Yes or no? Are you there, everyone?
Yes, sir.
Yes, sir.
So please do write it. Some basic terms, the definition, it's important. And do let me know when you are done with this. Whatever I just explained, it is written here.
Done, sir.
So coordination entity up to coordination entity done. Now come to this legend. And also write the
Yes,
coordination
sir.
number as well. Have you done this legend?
No, sir. Wait. Yes, sir. Done.
Are you done with this? Uh, Fawaz?
Yes, sir.
Okay, very good. No, see. We just completed our basic terms that is already explained. And there was one more term that is basically your coordination number, right? Yes or no?
Yes, sir.
So what is coordination number? So coordination number, I didn't explain this. Coordination number is basically number of or total number of coordinate bond between central metal atom and ligand. Central metal atom and ligand. As you have seen that K4 FeCN whole 6. So this is your central metal and this is your ligand. This is your ligand. How many ligands are there? 6 ligands are there. CN. So basically Fe, this CN has tendency to make only one bond, to make only one coordinate bond. This one CN can make only one coordinate bond. There are some ligands which can make more than one bond, which can form more than one bond. So as you can see, the coordinate bond between CN and ligand total are 6. So the coordination number of this compound will be equal to 6. Is that clear? Is that clear?
Yes, sir.
If I will ask, what is the coordination number of this compound? Can you tell me? Look at the compound and I think you can tell me.
2.
So coordination number equals to 2 because 2 ligands are there and the ligand is CN. CN has tendency to form only one coordinate bond. That's why coordination number equals to 2. Nafisa, have you got it?
Sir, can you explain again?
See, Nafisa, this coordination number is the number of coordinate bond between central metal atom and ligand. And CN, one CN can make only one coordinate bond. Are you getting my point? So if
Yes, sir.
6 CN is there, CN, that means this CN is cyanide ion. CN is cyanide ion. So if 6 cyanide ion is there, that means 6 coordinate bond is there in between central atom and this ligand CN, cyanide. So total 6 coordinate bond you can look at. So coordination number equals to 6. So what I asked, can you tell me the coordination number after looking at this compound? Officer, tell me.
2.
2. It is 2 because 2 CN is there and 1 CN can form only one coordinate bond. That's why. Now look at some of the examples. UNH3. It is whole 4 to the power plus 2. And there are some chromium H2O whole 6 to the power plus 3. And there is COEN, that I will tell you what it is, whole thrice to the power plus 3. And then Fe, C2O4 is there to the power 3 and plus 3 is minus 2 is there. Minus 3 is there. Minus 3. So see, the coordination number of this is equal to 4 because one NH3 can form only one coordinate bond. That's why coordination number 4. Here the coordination number is 6. That means H2O can form, one H2O can form only one coordinate bond. Here the coordination number is 6. Why? This EN is basically a didentate ligand. We will discuss about it, what it is. A didentate ligand, that means alone it can form two coordinate bonds. And its name is, it is short form that we use EN. Its name is basically ethane 1,2 diamine. Ethane 1,2 diamine, and we can write the structure of it. We can write easily the structure of this: CH2 NH2 and then again CH2 NH2. And here it can see, it can alone can form two coordinate bond. So if one EN can form two coordinate bond, how many coordinate bond can be formed by three EN? 6? Yes or no, Nafisa and Fawaz? I'm just telling you right now, just take it in your mind, and then when we are going to discuss about the ligands, please do respond, both of you.
Okay, sir.
Nafisa, Nafisa, are you there? And its coordination number is also 6, because this C2O4 minus 2 is basically known as oxalate ion. Oxalate ion, and it can alone form two coordinate bond, and its structure is C double bond, C double bond, and then O negative and O negative. It alone can form two coordinate bond. So if one C2O4 can form two coordinate bond, how many coordinate bond will be formed by three C2O4? 6 or not? Awaz?
Yes, sir.
Okay.
Sir, how
Please
to,
do
sir?
write. What I told you, this is oxalate ion, yes or no?
Yes.
And this is the structure, and I told you that one C2O4 can form two coordinate bond. So there are three C2O4. How many coordinate bond will be formed? 6, because one form two coordinate bond, so 3 form 6 coordinate bond. Okay,
Okay, sir.
please do write it. Please do let me know when you are done.
Yes, sir. John.
Done, both of you?
Yes, sir.
Okay. Now see, there are two types of complexes. Complexes are of two types. That means coordination compound are of two types. One is homolaptic complexes. Homolaptic complexes, that means the central atom is surrounded by same type of ligand. There is only one type of ligand present in a complex or a coordination compound, that is known as homolaptic complexes. So I'm going to write a definition. Write with me. Complexes which have only one type of ligand are called homolaptic complexes. As for example, we can take K3 FeCN poles, and if same type of ligand is surrounded, if same type of ligand is present, that is homolaptic. Another is heterolaptic complexes. Heterolaptic complexes. So what is heterolaptic complexes? So as you can see, complexes which have more than one type of ligand, are called heterolaptic complexes. As for example, we can take the example as CO, NH3 whole 4Cl. So if more than one type of complexes is there, that is heterolaptic, and if if one type of complex is there, that is homolaptic. Is that clear?
Yes, sir.
Please do write it.
Done, sir.
Done, both of you.
Yes, sir. Done.
Now we are going to discuss about classification of ligands. Classification of ligands. To see what is the classification, how we are going to classify it. So the first is basically on the basis of charge. On the basis of charge. So ligands are classified into three types. On the basis of charge, ligands are classified into three types. The first one is cationic. The another one is neutral, which has no charge. And the third one is anion. So as you can see, cationic, that means the ligand which has positive charge like NO plus, like NH3 positive, etc. And the ligand which has no charge, neutral, is like NH3, EN, H2O, etc. And the anionic like Cn minus, Cl minus, all the X minus basically, then comes C2O4 minus 2, etc. So this is the first classification of ligand on the basis of charge. Ligand can be cationic, neutral, and anionic. The less used ligands are basically cationic. Please do write it and then let me know.
Yes, sir. Done.
Fawaz, are you also done with this?
Sir, once. Done, sir.
Very. Now see, the next is on the basis of NTC, we classify on the basis of denticity. What is denticity? So first I'm going to define this denticity. Denticity is basically the number of coordinate bond formed by one ligand. There are ligands that can form one coordinate bond. There are ligands that can form two coordinate bond alone. So on that basis, we are going to classify this. The first is basically, we call it either monodentate or unidentate. Monodentate, or we call it unidentate. What it is, so as you can see, monodentate or unidentate. So the ligand which can form only one coordinate bond, that is called monodentate. So I'm going to write the definition right with me. Ligands having single donor atom. Single donor atom. Since coordinate bond forms, so unequal sharing will be there. One will have more electron, 2 electron it will have, and it will donate one of its electron to central metal atom and then make bond. So the ligands which have only one or single donor atom, that is monodentate. As for example, we can take Cl minus, we can take Br minus, as well as NH3 and etc. As you can see, NH3 has one lone pair, so it has one donor atom, so it is monodentate. Please do let me know. Nafisa, are you done with this?
Yes, sir.
Very good. Now see, we have another type of ligand, that is didentate. The second one is didentate. And didentate, that means, or bidentate we can call. We can call bidentate as well. So basically what it is, it's very easy to understand. Ligand having two donor atoms or ligands which can form two coordinate bond at a time. Two coordinate bond at a time. That is called bidentate. As for example, we can consider the example of ethane 1, 2 diamine. Ethane 1, 2 diamine. So as you have seen, its structure is like this: CH2, CH2, and there is CH2, and then comes NH2, and this is also your NH2. And you know, nitrogen when makes 3 bond will have a lone pair. So it can donate from here as well as here. So that's why it is didentate. As another example is oxalatine that we have already discussed, has a formula C2O4 minus 2, and its structure is like C double bond O negative, and then again C double bond O negative, and you can see it can donate from here and here. So it is didentate. Everyone. Please do let me know when you are done with this.
Yes, sir. Done.
Very good. Pause. Pause is not. Okay. So after bidentate, we are going to discuss about polydentate. That means that makes several, which have several donor atoms. So we can write polydentate ligands having several donor atoms. Several donor atoms. That is called polydentate ligand. As for example, the most famous is basically EDTA4 minus. This is a ligand EDTA4 minus. So as you can see, its name is basically ethylene diamine tetraacetate. Ethylene diamine tetraacetate ion. And it has a structure. You can see it is basically hexadentate. It is basically hexadentate. That means alone it can form 6 coordinate bond. Its structure is like this: CH2 and then CH2, and then nitrogen, and then also nitrogen. Then comes CH2 and then COO negative. 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 Now come to this point, you can see it can bond, bind through this, make bond through this, and also through this and this. Alone it has 6 donor sites. That's why it can bind through 6. Is that clear?
Yes, sir.
Please do write it and let me know. Let me know when you're finished with this.
Yes, sir.
No. Then the last ligands classification is basically ambidentate ligands. Ambidentate ligand. You see, what is this ambidentate ligand? Basically, this is a special kind of ligand which have two donor site, but it will use only one at a time. So we can write ligands which which can bind or which have two donor site, which can bind through two different atoms, but it will use only one at a time, only one at a time to form coordinate bond, to form coordinate bond. And this type of ligand which has two donor atoms, but it will use one at a time. This type of ligand is known as ambidentate ligand. As for example, NO2 negative, SCN minus, etc. So now see, let's say this is your central metal atom, and this NO2, we are going to take an example. NO2 has a structure like this, NO negative, and this is basically lone pair. So basically it has two donor sites. You can see either it can donate from here, but it will use only one at a time. It will use only one at a time like this. Or if it will use nitrogens, it cannot use this. Or if it will use oxygens to donate or bind to central atom through coordinate bond, it will not use the nitrogens. Is that clear? Nafisa?
Yes, sir.
So this is it for today. After this class, tomorrow's class will not be possible. Okay, Nafisa?
Yes, sir. Okay.
Okay. So in the